Yeah. All right. So I think we can start. So thank you for coming in, Mr. Arshad. Uh, would you please introduce yourself a bit?
Yeah, sure. Yeah, thank you guys for coming to this meetup. My name's Arshad. And I'm basically a software developer, and I developed in a lot of different programming languages. I'm reasonably new to embedded Rust, although I've been working in Rust for a couple of years. And it's my favorite language now, and it's the most passionate I am about it. But over my career, I've done everything: C, C++, Java, Python. But yeah, Rust is where my head and heart is these days. So today we're going to be talking about a particular class of devices. So these are slightly more powerful than microcontrollers. So particularly the NVIDIA Jetson. There's quite a few in the range, and we're going to be talking about the least powerful and the cheapest one, which is the Orin Nano. It's still a pretty good device because it's got an ARM CPU and an NVIDIA GPU, a slightly older one, an Alpine class one. And it's not obviously as powerful as the recent ones, but the software support is still pretty good. And you get quite a powerful machine for about $250, 8 gigabytes of RAM, and it can do about 10 trillion operations per second, which is perfectly fine for like a lot of different workloads. And people do use it for like robotics and a lot of like embedded vision type stuff. It's probably the most popular kind of in those kind of industries because it's NVIDIA and it's had quite a kind of like a stable software development environment for quite a while. So there's a lot of people invested in it. And I chose it really because it had a nice sweet spot. It has good Rust support. You can actually install the Rust toolchain on it if you wanted. But I am not going to do that. I'm going to use cross compilation, and because that's what I'm interested in. But anyway, so let's begin. So just move to the screen. So the outline of what I'm going to be my talk today is going to be first of all defining what the problem is that I'm trying to solve, and then why this matters for embedded Rust, and then my particular solution to this problem, which is this thing called Tinigrad. Then I'll give you an overview of the architecture of Tinigrad, key technical wins you get with this approach, the performance of it today, and the trade-offs that you have to you make by going down this route. Then I'm going to do a demo, which is YOLO 26, which is one of the newer vision models on built and then cross-deployed to a Jetson or a Nano, and then have it running actually on the Nano with an AI demo, which is the parking garage demo. And then I'll give some lessons and trade-offs and some resources at the end. So that's kind of like the outline of this talk. Please feel free to ask a question if there is at any point where something's not clear or you just wanted to ask something. Yeah, don't feel hesitant about doing that. So with that, so let's begin. Okay, so a lot of you guys, I guess, are still working with just getting hardware working for you. But once we're over that, and we've got particular microcontrollers with good ROS support, really the next frontier is actual applications on those devices. Now here I've summarized some applications currently with embedded hardware. So it's robotics, drones, video analytics, which is real-time analytics, say from traffic cameras and things like that. Internet of Things and smart devices in the home, like cameras, sensors, autonomous systems in cars, and then industrial inspection. So the software for virtually all of these right now is actually C, C++. So the actual applications are written in C, C++. Virtually all of them do need AI. So typically the AI is done in Python. And so it's written in Python, trained in Python, and then it's exported to like a common format like Onyx, which is like an intermediate format for being able to take models and run them on these kind of devices. And each of these devices got its own kind of runtime. Onyx runtime is a reasonably standard one, so that'll take one of those and run it on one of these devices. But long story short, there is this kind of pipeline you have to do. So the code you have to write is in Python, you have to export it, you have to copy it across to these devices and then integrate it into your C, C++ application. So whatever that is, your robotics application or your IoT application. And what I'm trying to do is really get rid of all that C, C++. I would really like all of the code that's on these devices to be written in Rust, so that it's memory safe, easy to debug, has got good performance, but you still have great kind of software development ergonomics. So all the things that we like about Rust, great compiler messages, and all that kind of stuff. So yeah, so what I want to do is, if anybody wants to say develop an application for a drone or a robotics, that they give Rust a serious consideration instead of going straight for C++ and saying, yeah, that's the way we've always done it. Let's use Rust instead. And the bedrock of that obviously is device support, which is critical. But more devices are getting support now. So this is now a practical sort of option. So next, so as I said, the problems are the AI models and edge devices require a build pipeline. So you have to write it in Python, export it, quantize it, have an actual runtime on the device which runs, and then integrate that runtime into your C++ application. So it's a bit of a palaver, and it's all legacy C++ code. So as it says, typically Python is used for the AI model, and then you export it and run it on the device. Jetson 9 is quite a powerful device, so I'm giving this as an example, and it's got really great raw support because it's an ARM chip with an NVIDIA GPU. Both of those, they've got good C libraries which you can link into from Rust using BioJet. It's reasonably cheap, about $250. In the scheme of things, I know that's still quite a lot of money, but you do get actually a pretty good device for that, which can do a lot. And as I say, deploying models usually right now means you've got a Python dependency, and and then you have to do some other degree pokery to get it running. Even on a RN Nano, you have to. Its native runtime is called TensorRT, and then that requires you to take your model and then kind of JIT compile it using a TensorRT compiler, and that'll give you something that then TensorRT can actually run, and you integrate with it using C++ code, and that's one approach. You could install PyTorch on an RN Nano, but the problem is that the newest versions are usually not available. So you are looking at a slightly older version of PyTorch, which has support for it, because the device is specific. PyTorch has to add support for it, and they don't always do that. So the pure PyTorch Python route is not always available because it's lagging kind of behind. So anyways, it's a bit of a mess, and a lot of it's legacy code, C++. So why this matters for Rust? So we've actually got quite a compelling kind of case for why people should be using Rust. First of all, it's much easier to program a complex kind of system, I would say, in Rust, really because of the compiler and the great error messages you get, and the fact that it protects you from all sorts of memory errors, which C++ really doesn't. I mean, obviously you could code in a certain way and use certain libraries to help you, but even then it requires a lot of discipline, and you're fighting against the language, really. And then you got memory safe to be that garbage collection. So in a lot of these kind of embedded systems, predictable performance is very high on the list. So typically, you wouldn't want anything that needed a garbage collector because you just couldn't guarantee any kind of real time kind of timing guarantees on things. But the problem is all the ML stuff right now lives in Python ecosystem. So they're completely different types of developers. So the ML guys would be Python, and all the guys who are writing the actual applications on the system, C++. So it's two different groups of people having to do this. But wouldn't it be great if you could just do everything in Rust? You could actually write your application in Rust. You could write your AI models in Rust. You could test them all on a host because it's the same kind of SDK you're using. And then once you've done all the testing and debugging on your host, for instance, for an NVIDIA GPU, then you could just deploy it, and you'd be pretty certain that what you'd actually deploy to your device was going to work pretty much first time, basically, because you had done a lot of thorough testing on it. So long as your tool chain kind of supported that compatibility, that the two, you could guarantee that they were going to do the same thing on the two devices. You would still have to do manual testing, but the amount of manual testing you would have to do, I mean, compared to what it is now, where you have to actually had to do all the QA on the device, but all the dev was done not on the device. It was done on something else. So yeah, there's a lot of pain points in this system right now, which you could fix if you could do it all in Rust. So what's Tinigrad? So basically, Tinigrad, originally the inspiration was Andre Karpathy. He actually created he's got actually a YouTube video on it. It's called Micrograd. And I think he built it over a weekend. It was basically from first principles, a tiny little ML framework that he built in Python. And all it showed you was how does like a compiler like PyTorch work? So how does it take a neural network and how does it kind of like compile into something that actually runs a neural network? How do you train it? And from that came a project that George Hotz created, which is called Tinigrad. And that's actually still in development, although he's more focused on inference and AMD GPUs. So he's like right at the other end, data center type stuff. And he actually sells hardware as well, quite powerful hardware to go with that. But I was interested in doing Tinigrad, but in Rust, and trying to make it as minimal as you could. So you could run it on edge type hardware which had a lot less memory, a lot less compute. But the future, and this was about a year and a half ago when I started, it looked like it was going to be that modern processors would have CPUs and NPUs integrated. So the idea was that there'd be a CPU which would do all the normal work. And then there'd be some dedicated stuff to do AI. And these would be your matrix computations and your vector computations. And right now, there was no kind of framework that could deal with that. Basically, they were either all CPU or all GPU. And what I was looking for was something which could do a bit of both. So I kind of looked around for what was available, and I chose one particular approach, which is called Triton. And that actually already had a quite good C++ library using LLVM as a compiler. So I built my sort of system based on that. And the advantage of that is that I get good integration with Rust through that LLVM toolchain, but I can write custom sort of backends for different processes. So for instance, right now I'm looking into creating a backend for RISC-V processes because I'm quite interested in how that's evolving. So that's kind of the history of Tinigrad. It was kind of inspired by George Hotz's work because I was originally going to extend Tinigrad, but because it was Python and I despise Python, I dislike Python. I've always worked in strongly typed languages, and I just don't like duck typing. So that's why I built Tinigrad. And but I wanted it to be able to kind of like compile down to all the hardware capabilities that you had available for a particular GPU or a CPU. So for instance, modern RISC-V processors, they have standard vector units, but now some of the manufacturers are starting to add matrix units as well, or extending it slightly. So the Spreadme K3 is quite an interesting one. And I'm actually due to get the hardware for that within about 3-4 weeks because unfortunately it's on back order. And that seems like quite an interesting processor within OpenISA that I'm looking to work on. So that's the history of it, kind of Rust, capable of targeting different types of hardware and making it so that you could write custom code for each piece of hardware to get as good performance as you possibly can. So that's kind of like the history of the project. So the architecture. So basically everything is in Rust. So there's no Python in here. So you actually write your machine learning model in Rust. You write your training routines in Rust, your inference routines in Rust, or you get it from the library in Tinigrad. Right now, we don't support Onyx. So basically, you would have to write your AI model in Rust. But within Q4, what we'll do is we'll take an Onyx model and kind of give you the Rust that you would need to be able to run it using our framework. So you'd get free support for all the Onyxes that's currently in PyTorch. So that's our way of kind of integrating with the PyTorch Python ecosystem. So you can compile and test it on a compatible host. So for instance, if your host has got an NVIDIA GPU, then you could compile and test your model on that NVIDIA GPU host. Currently, we only support Ubuntu, but we could support anything that Rust runs on because ours is kind of like a custom Rust compiler. So we forked the Rust compiler and added all this stuff to it. And then you can, once you've done all the testing, you can cross-compile it. Right now, we support the Jetson Orin Nano using Cross and the compilation for ARM support in Rust. And then we kind of package it up into something that's 6x friendly. So this is like a little tiny file system. So you got to buy, which you could then package using Yocto. But right now we just copy it using rsync to the device for testing. But you could package it using Yocto or any other kind of packaging tool to create like an actual kind of like an image which you could install on the device. What we're trying to do is to get the code to be one binary with no additional dependencies. Right now, the kernels, which are basically the GPU code, they are emitted in a folder on this when we package it, but they don't necessarily have to be. We could actually package them with the binary so that they're actually embedded in the binary. But right now, that's just convenient because we can look to see how many whether the kernels were correctly generated, and how we look at them to see their code to see what that looks like. But that's just like as I said, is how it's packaged will sort of evolve as people start to use it. It's still slightly pre-release. So I've just released in the last 2 weeks, so it's still very early days. So, but that's kind of the way it is. So key technical wins. So we can generate right now kernels for virtually all the NVIDIA hardware going from Ampere. So if you know anything about NVIDIA, this is kind of good, quite old. So all the newer hardware we can cope with, and then we go up to Ampere. No Python. It's a small binary with all the model and the runtime and everything. It's about 25 megabytes typically. Depends on your application, obviously. If your application is quite big, it could become bigger. But our own code is about 25 megabytes. It's pretty quick startup, as you can imagine with Rust. Predictable latency because there's no JIT at runtime. It's all precompiled. And you can integrate with existing C++ libraries. So if you use kind of like BindGen, which I've done with GStreamer. So basically, for those of you who haven't heard of GStreamer, this is NVIDIA's video interface. So you can connect a camera to it. It'll decode the camera stream and give you frames, which you can then obviously pass through to your AI model. So this is called GStreamer. It's a library basically, but it's a C++ library. But you can, but it's pretty easy to integrate with Rust through BindGen. So that's kind of like where that is. So the performance trade-offs. So compilation is a bit slow. So typically for cross compilation right now, it takes maybe 5 minutes to create the full package for a cross-compiled binary to a device. Binary size is very small, about 20 megabytes. The actual performance is not competitive with the native frameworks right now. So things like TensorRT is a lot quicker. And basically, I know why that is. So basically, TensorRT, they generate code for each specific device. So it's hand-tuned. But there's quite a lot that I can do. So right now, it's about 7x slower, which sounds horrendous, but actually even in Onyx runtime, which is the industry standard, is about 3x slower than TensorRT, which is the fastest because that is NVIDIA's own code. But there is quite a lot of work we can do to bring that down. I think we can get it down to maybe it's about 2 times slower. We can probably never get it down to TensorRT because that is hand coded for that particular device. So ours will work across because of the way the code is written. Even though it targets NVIDIA hardware today, you could target AMD hardware tomorrow and RISC-V hardware the day after because the interfaces you're not coding specifically to CUDA. You're coding to the SDK, and that's portable. So because of that portability, we can never really get to the performance of the specific hardware implementation. Although that's only really the case for TensorRT because virtually all the other hardware manufacturers, if you're talking about the Qualcomms of the world or all these other NPU providers, they all provide Onyx runtime. They don't really provide typically these really device optimized runtimes like TensorRT. They tend to just port an industry standard like an Onyx runtime. So we could probably beat those sort of within, I reckon within this quarter, we could beat that. So where it shines, embedded, latency critical, and offline scenario, because we build on the host and just deploy it. When it's not ideal, if you need to do rapid iterations. So if you're making a change, you want to deploy it to the device, test it immediately on the device. Typically, it'll be probably between 2 to 5 minutes on each of those iterations because it takes a little bit of time to actually package for the device. I haven't optimized the compilation speed on it, so probably we could get it lower. But right now, as I say, it's not an issue for me because I do all my development and testing on a host, which has got like full cache. But typically, if you're building on the cross, then because it's in a Docker image, you won't have the full cache. It will build it completely from scratch. So that's a little bit slow. So kind of that's kind of the trade-offs. So I'm now going to do like a demo effect. Okay, and let me just sorry. And let me bring it across. Okay, so what I've done is I've created some instructions here. Okay. Now, so what I'm going to do is I'm going to first of all, there are some prerequisites that you need on a machine. So you need an Ubuntu machine. It needs to have an NVIDIA graphics card, a reasonably recent install of Rust. So I'm going to be using 197.1, which I actually just did Rust update this morning, and a CUDA toolkit installed. So probably recommend the latest one, which is 13.3.1. So my Mac, I'm actually connected here over SSH to a Unix host that I run for my development because it has an NVIDIA GPU. It's not very powerful. It's just a 5070, which is like a cheap NVIDIA GPU that I've got on my development machine. Now, the first thing I'm going to do is I'm going to install a cargo command, which is a CLI that derives a lot of the development. So I've actually already got it installed, but if you did cargo install cargo tiny, by the way, these instructions are available on the documentation side for getting the demo up and running, and it's in the resources section of the slide as to where that is. So because I've already got that installed, but it only typically takes 30 seconds to install, it's not a very large application. The next thing is that we're going to need a tool chain. So basically, this is the custom compiler. And again, for Ubuntu, it's pre-built. So this is just going to download it and install it. So this is a pre-built binary downloaded from the CDN that I've got hosted, and it link it as a tool chain locally. It's a custom tool chain, so it's not really meant for like compiling Rust. It's meant for compiling our code. So it's got a special name, TinyC. It's not Rust C. So it won't clash with your existing tool chains for Rust. So that's the first two. And then I'll clone a, so there's a Git repository with a Vision SDK, which has actually got an AI model example written in Rust and some demos. And that's this Vision RS. So if I now go into that, and what I will do is I will then copy and source an environment. So there's an example environment. It's pretty simple, really. All it's got, the TNC is if you're actually building a custom compiler and want to test it with that compiler, but you can use the one that we've just installed. And the only thing it needs is where to cache the data sets and where to cache the models. Because currently we work with the Ultralytics YOLO models, so we don't train our own. And we use whatever data sets we need, where we should cache those. So by default, we do it in $home, but you could set it to a different directory if you've got a disk where you would rather have that. So, and then now I will actually build the examples. I've only got one example at the moment, which is running YOLO 26. This should only take about 30 seconds to build. So we'll let that build. And while I'm waiting for that, I will, this is it running. So I will, once it's built, I will run it. So what this is going to run is the YOLO26 example, the view command on it, because it's got a couple of others, benchmarking and the verification. The model, which is the YOLO26 nano model from Ultralytics, and the data set. I could have actually just before I didn't run the download the data set, which you do need to do, but I've already done it on this host, so I'm not going to do that. But anyway, the data set is cached, so okay, that should be finishing pretty soon. Okay, and now I'm going to run that example that I just built, and this is okay. So what you're looking at here, so this is all written in Rust. So this is using one of the crates to give X Windows support, or X Windows support. And what this is running is an image through a image classification task. Also, no, object detection task. So here it's detected a person, which is this big box, and then a cell phone and two cell phones. And you can use the arrow keys to go forward and back in the. So the data set I've chosen is COCO 128. So this has got 128 images from the COCO data set. It's one of the famous data sets in image classification, basically. So 2 bears in that one. So books in here and a person. So this is just showing that the model was written in Rust. The application, this application which you're seeing is written in Rust. And it's all running on an NVIDIA GPU. So this is actually using the GPU for the inference. And that's pretty much it. So yeah, so it took probably sort of 5-10 minutes to get going. So that was on the actual host. So that's on my Unix box, which is reasonably beefy. Well, it's got 32 gigs of RAM, but the processor is quite old. And as I said, the CPU is the GPU is not very powerful. Now, so what I want to now do is to, in this particular project, the Vision RS, I have got some demos, and actually, currently there's one demo, which is the parking guide, but I'm going to add this. What we're going to now do is to package that demo for the Jetson or in Nano. So this is that command. So what this is using is cross to compile the application. I couldn't run it on my Unix box, which I was just on the other one, but I actually want to run this now on the device rather than on the host. I did the debugging on the host, but now I'm ready. I want to actually deploy it to that and get it running. Now this is going to take a little bit of time to compile. Because what it does is it compiles two applications: a server, which does all the inference and publishes the objects is detected over WebSocket, and then a second application, which is a web app, which actually listens on that WebSocket for new object detections and renders them on the screen. So it's a client server application. With JavaScript in the browser. So it's quite a complicated application. Everything written in Rust, except for the pure JavaScript. But the web app is using Axum. And you can see the code, but as I said, there's no Python or anything like, C, C++, and it's all written in Rust. It also will build it for the host, because what it's going to do is it's going to get it to compile the ML model ahead of time for the device. And this is why it's going to take a bit of extra time. While it's doing that, instead of sitting here waiting for it to kind of do that, if I kind of move on and just do a couple of these slides while we're waiting for that. So the lessons and trade-offs. So Rust strengths are safety, deployment simplicity, and predictability. So you get the build environment is fantastic, no dependencies, you get a fantastic compiler, great dev environment in VS Code and with Rust analyzer, so all of that. And that includes the ML model and the kernel, so everything's statically typed. So all of that is kind of like a really great developer experience. The kernel limitations are, so the kernels are hard to write and debug. Now, so basically the kernels are written using a DSL called Triton, which I've created a Rust kind of trait for. and you're writing to that trait. So you do need to know how Triton kind of works, exactly how you express your kernel, and that's non-trivial. I'm going to try and create videos for how to do that so that people can learn how to write their own kernels for whatever crazy stuff they want to do. But that's actually true whether you were writing in Python, if you were writing your own kernel in Python, or if you were writing in CUDA, that's always hard. But I haven't made it any simpler, basically. It's just as hard in Rust. You do get a little bit of help from the compiler because it's all statically typed, whereas obviously with Python, you could be writing all sorts of crap, and until you run it, you won't know. But at least here, the compiler will tell you, hey, this is not, this is invalid. But obviously, to actually write a kernel is non-trivial. And Rust type systems doesn't make it always the easiest because the compiler type error might be pretty cryptic. So there will come a point when I will need to work on a kind of clippy to really help you out, to add new clippies to really help you out with what's wrong, why you did it wrong, and things like that. But that's not true right now, so that's pretty hard. Also, unit testing is very limited. You need hardware for testing, basically, because the kernels need to run somewhere. Actually, when I originally created the framework, unit testing was one of the main reasons I did it. So the idea was that I have a trait, and I have an LLVM implementation of that trait, which is the stuff that compiles for the GPU. But I should be able to create an ND array implementation of that trait, which should allow you to do unit testing within. So that's to do. So that's going to be coming at some point, and that will make all of your coding and testing, 10x easier because you won't need to constantly go to the hardware. You should be able to do good, robust CI. But right now, that's not true. All your testing needs a bit of hardware, which is a bit of a pain. What works today? Strongly typed kernels and AI models. So the kernels are not easy to write, but they are strongly typed, and the compiler helps you a lot. Great development environment with VS Code and Rust Analyzer, which is not the case with C++ code because of Rust statically types. And Rust Analyzer, you get a fantastic development environment, and you get ahead of time compilation, which just means that the binary you deploy to the device, it doesn't have to have all sorts of compiler crap and JIT crap in it, because everything's done for you ahead of time. It can be a pretty lean thing that you actually deploy to the device. What's still evolving? Well, performance is not fantastic, but I know exactly what the issues are. So some of them are easy to fix, some of them are not so easy to fix. And quantization support is missing, and it's actually critical for Edge, because basically, typically you would develop it using FP32, because that gives you the highest precision. But unfortunately, a lot of models that on FP32 won't fit on an edge device. There's just not enough memory. The GPU is not powerful enough. So typically what we do is we quantize it down to either FP16, FP8, or int8, or maybe even int4. So that support is really needed for it to go into production, and that needs to come. And as the hardware support is limited, particularly for edge kind of like processors. Unfortunately, the hardware guys don't make it easy because they don't publish ISAs. I don't know why they don't do that. It just seems like for any CPU they release, they publish an ISA, but for any NPU, which is the AI kind of engine in a lot of these devices, they just don't. RISC-V is the only one which is different, touchwood. So yeah, that's what I'm going to prioritize is RISC-V support going forward for any processors, because I think within the next couple of years, there will be quite a lot of edge being done. And I've been talking to a Chinese system on chip manufacturer who are actually doing a new generation of RISC-V, and they do industrial system on chip kind of like solutions. So if they, as I said, they don't know if my stuff's mature enough or whether it fits in well, but they might be interested in getting compiler support for their processes. So that would allow me to get access to all the kind of like hardware knowledge and ISA knowledge and engineering support to be able to do it. But I'm committed to doing RISC-V support anyway, so that's what I'm working on. So that's where that is. Resources. So I provided some links here to how to where the project is, where the docs are. The docs are still work in progress. So if anybody looks at it and there's some errors, do please let me know. And there's a Discord. So if you do fancy playing with it and you're having problems, join the Discord and I'm there. So just ask me questions. And while hopefully that we've made some progress and finished with that. Right. So that's actually finished compiling now. That took a couple of minutes. It obviously takes a lot longer when you don't look at it. So what I'm going to do here is, so basically this is deploy. So what we're saying here, so that first off is package, and it said, can you create, so I can actually show you what's in this guy. Oops. So what it did was it created a packaged application in this fellow. So you can see in here, it's got bin, cache, conf, and data. At the moment, conf and data are not really being used, but the idea is that so if the application needs a configuration file, that's where it should go. And if it needs any data, that's where that should go. So, and this file system is what you would include as part of a Yocto image for this application. If I look in bin, which is where the binaries are, there's two binaries here. So the parking garage server, which is the guy that actually loads the images, does the inference, and publishes what it's detected onto a WebSocket. And then the parking garage web app, which is just a web server with a kind of like a page with an embedded view application. So that's Vue, which is one of the JavaScript frameworks, to be able to listen to those WebSocket publishings and actually display it on the screen. And I'll actually show you how big they are. They're not very big. So the server is the bigger one. That's the one that's doing all the work, and that's about 21 megabytes. And the web app is about 4.5 megabytes, so pretty tiny, really. And the only other folder that's of interest is actually cache. So this is actually all the code for the GPU. So all of these are basically kernels. Kernels are basically programs that execute on the GPU. There's multi-files each, but the .o is basically what's going to be on the actual device. The .rs is the Rust that got compiled to that. So there's 3-4 files each. There's a .mlir, which if you're interested in LLVM and how it works internally is what you would look at. The .rs is the actual original Rust, which got compiled to MLIR. And then the .o is the actual GPU code that will be executed on the GPU. And the lock file is really just there to ensure because you can run the compiler on different files in parallel, that doesn't happen basically. So that's sorry. So that's that. Okay, so we've got it all kind of like packaged up. Now we need to ship it to the actual device, and we use this command, which is called Watino deploy, and you tell it where the package is, the host, which is username, password. In my case, it's called Orin, and because I have SSH authorized keys enabled, I can just use the host name, the destination on the host's, on the device where the package should go, and I've done override because I've published it a couple of times, and I'm going to override to this one. So if I execute that, so that's actually pushing it to the device. So my device is connected, it's called Orin, and that's actually copied it to that guy. Now I will SSH into my Orin. I've got two tabs here. So because we've got two applications, a server and a web app, we do need to SSH Orin. Okay, and then I will also do a second one, SSH Orin. Okay. And then in here, so I will go into Parking Garage. Now, you do need to create a .env file, which unfortunately at the moment is, basically it overwrote, what the override does is any files that have changed it overrides, but it doesn't delete anything that's already there. We could probably add that. But anyway, just like we had, we need a .env to say where the models should be cached, which is not really being used. But basically a couple of variables which are needed for the application to run. It needs two ports. So I've actually enabled the UFW firewall in here. So obviously on your device, if you don't have firewall enabled, then that's okay. Okay, and then just sudo password. But if you have a firewall, you're going to need to open two ports, which is 3000 and 3001. These are the server for the WebSocket and the web app for the HTTP server for the web app. So what I will do there is I will now run the server in this tab. And all it is just /bin/parking garage server. It's a binary, all statically linked, no dependencies. You can just run it. So what that does is, now the very first time you run it, it does need a data set. It's called the parking lot data set. If it doesn't have it locally cached, it will actually grab it. It is a kind of a large data set. It's about 4.5 gigabytes. So it does take a bit of time to download the very first time. But then it caches it, so you won't need it a second time. So that's the server up and running now. And I will go into parking garage as well and run the web app. Again, ./bin parking garage web app. And so that's those two server applications are running. Now on my Mac, because that's exposed outside the, so if I go back to that, actually, what's that? Full screen. Yeah, let me go back. Okay, so if I now go back, I've got demos and I've got parking area. Right. So now Orin, okay, let me just, yeah. So I've gone to Orin port 3000. So Orin is the name of my Jetson host. Port 3000 is the port that the web app's running on. It uses the 3001 itself to be able to connect to the WebSocket. That's why you need both those ports open on the firewall. But yeah, this is it running on the Orin packet parking garage. It's grabbing an image at a time from the data set, running inference on it, detecting the cars. The parking lot data set does tell you, it only annotates a limited number of parking spaces. That's why not all the parking spaces are covered. But as the cars come in, if the car is detected, it marks that parking spot as occupied. And that's the original YOLO 26 model from Ultralytics to do that. This is an end-to-end, everything in Rust. The web app's written in Rust, the server's written in Rust, the model's written in Rust. There's no Python anywhere. It was all. So this is pretty much what the capability of the system is right now. For this kind of application, the performance is perfectly fine. It's actually more than fast enough. But obviously, for really real-time drone work, we need to fix the optimization, really. And that's kind of me. I don't know if anybody's got any questions.
Yeah, so we'll start the Q&A session. If anyone has any question, you're free to unmute and ask any questions.
I hope I haven't confused the hell out of everybody. That made sense.
That was a very good explanation. Thank you. So somebody's typing
No,
something in the
actually, I
chat.
was going to type the question, but I feel I should just ask. So, it is actually a very relevant project to me. I also, sometime back, built a image detection pipeline on Jetson Nano, but I mean, couldn't get enough throughput. My question is, is your choice of using Jetson Nano, is it because you had it already, or does it provide any particular value? I'm particularly intrigued, when I compare these to modern SBCs that have NPU, like something from Ratsa, right?
To be honest with you, it was at a startup's budget. I wanted the cheapest device that I could buy because I didn't want the framework to end up being, well, you can only run it on a device with so much memory and so much disk space. Because the whole aim was to be able to run it on as small a device as possible. there's nothing special about the RN Nano really. It's the least capable of all the Jetson devices. The only thing, obviously, is because it does have an NVIDIA GPU that massively helps to code against it because it's the standard. But yeah, no, it was just the price of it, and it was more than good enough for what I was interested in doing on it. No particular device capability. Although obviously for me, the fact that it was able to run a kind of Ubuntu, although even that is not really relevant. It's just the hardware that I was able to, because currently I support NVIDIA type hardware. Anything that I could ship something NVIDIA related to was okay for me. And as I said, the cheapest one I could find was the RN Nano. That's the main reason.
Okay.
So what was the
you?
issue with yours? You were saying the throughput was not great.
Yeah, the
Uh,
FPS wasn't very good actually. I was building it for Slam robot, where it has to scan the environment, and localize itself. And there
and
it
what
was
kind of
too.
latency in the detection did you need?
Um, I mean, I could have managed by slowing the speed of the robot, but it was, I think, less than 10 FPS for my case, which was too low.
Really? And was that the which was it one of these or in nanos, or was that a slightly different?
Jetson Nano. That was Jetson
Okay.
Nano.
And if you don't mind me asking, were you using how did you code it? Were you using an Onyx export onto the Jetson, or was there like I don't know if you remember like how you were coding it?
Yeah, it was actually 4 years ago, and I don't think they were at that time there was Onyx. I don't think actually. I'm not sure. So it was just uh, OpenCV and some other stuff.
Okay, OpenCV. Okay,
Yeah,
okay, okay. That's
I
probably
don't remember.
CPU
Yeah.
if it's OpenCV.
Mm.
It I don't think OpenCV has support. Well, I may be wrong. Yeah, it has GPU support. Uh,
Mhm.
but but yeah, I mean, obviously, as I say, mine is. I think I had some statistics somewhere as to what frame rate I could get. It was about 10 frames per second. Uh, on my, although there are different. Obviously, I'm doing object detection, but there's segmentation of some of the models as well. I'm not quite sure about that. But anyway, the Tensor RT, which is the highly optimized NVIDIA, would get like about 8 times that more than that. So that would be 80 frames per second for theirs. But I know mine's the slowest because of the way it works right now. And there's lots of things I can do to improve it. But 10 frames per second should be like that should be definitely doable. But as we say, maybe the software and the hardware were like older and it wasn't possible. But OpenCV, I can imagine that wouldn't be great. Yeah. It really needs to be a proper
Okay.
AI model that's compiled down to the GPU.
Mm. So, do you do any optimizations on the model side also, or only on the runtime side, like Onyx?
So, I mean, what I'm trying to do is for the compiler to automatically optimize the model. What I mean is, so if you create a object detection model, it's quite a complicated model. It's got lots of different steps in it. Different convolutions happening, batch norms are happening. There's SILUs or different activation functions are happening. There's all sorts of stuff happening basically. And the number one optimization you can do is to collapse some of those. So that's called operator fusion. That's to, instead of having to do those individually, you kind of merge them together because they're kind of like a certain operation followed by a certain operation followed by a certain operation, just kind of squash it all together. Because actually the slowdown is all about transferring memory to the device and bringing computations back from the device and doing the next thing in the step exactly the same. So if you were to compare how much time the GPU is doing actually calculations it'll probably be 5% or less at the time. The other 95% is all the going backwards and forwards, copying data from memory to the device, copying the data from the device back to memory, because obviously that's having to go through a much slower channel than within the GPU chip. So if you can kind of, and it's called basically operator fusion. If you can do the fusion properly, that's how TensorRT gets its performance improvement, is because it does very aggressive fusion, because it knows exactly what hardware it's on and what it's capable of. So right now, that's what I'm working on, is this operator fusion, this kind of collapsing of the model into much smaller but kind of bigger chunks. And that should improve performance quite a lot. So yeah, and the other optimization you can make is to quantize, which is instead of doing it on full floating point 32, you do it on floating point 16 or floating point 8 or even integer 8. And you still get performance that's probably 97%, 98% of it, so you don't lose a lot. But the performance is obviously improved massively because the calculations are done at much lower precision. So between those two, you can get massive performance improvements.
Okay, yeah, that answers. Is there any way of following up on like the stuff that you're doing on model optimization?
Yeah,
I mean,
I
if
can
there's,
I can post my LinkedIn. I try and keep. I got a newsletter which I publish weekly about what I'm doing and what's happening. Um, or you can just join the Discord if you're like. It doesn't get. There's not a huge amount of traffic on it because I already set it up like a few months ago, where I might share what's happening. But I don't want to spam people, to be honest. But so the newsletter is one, and the Discord is the other. If you do genuinely just want to talk to me,
oh, okay, sure.
just as a matter of interest, what kind of work do you do now? Are you still in AI, or are you doing something else?
You asking me?
Yeah. Are you still working in robotics, or have you moved on to something else?
Yeah, that time it was for a startup. It didn't work well. Currently, I work in AMD as a system level engineer.
Okay. Uh, Yeah, AMD are very good about publishing their ICEs. I haven't looked at any of their edge hardware, to be honest, uh, yeah, very interesting company.
Mhm.
Does anyone have any more questions? You're welcome to post your questions in the chat too if you're not able to unmute or something. I'll read it out.
Cool. Yeah, feel free to connect with me on LinkedIn. It's on my profile on Discord if that's your platform. But if not, yeah, just anywhere on. If you just want to post on Discord, I'm on most days.
All right. It doesn't look like there are any more questions. So I think we can end it here. Thank you so much for
Great.
coming
Well,
in,
thank you very
Mr.
much, guys.
Yeah, thank you so much for coming in. We hope to hear more updates from you in the coming meetings. So, thank you so much. Thank you for everyone. Thank you everyone for coming. Hope to see you in the next
Great.
one too.
Thank you. Right. Bye, guys.
Bye. I'll end the meeting now.